Hello everybody and welcome back to another visual pattern challenge. Got kind of a doozy for you today. Here's our pattern. Here's step 1, step 2, step 3. Your job, your challenge is to predict the number of squares in step 4. If you can do that, can you predict the number in step 43? And can you write an equation that could be used to predict the number of squares in any step at all? So that's the challenge. If you'd like to accept it, pause the video and see what you can do. All right, so we've kind of got this weird looking S or Z pattern of squares, and it's getting bigger pretty quickly. I would bet this is quadratic for sure, maybe something more than quadratic, but I think quadratic because it's a rectangle that's growing. Um, you could try cutting it up into pieces, but I think maybe the best thing to notice is that these chunks taken out of it stay the same, right? There's always 1, 2, 3, 4 squares missing from each one. So I think I'm gonna think about these as rectangles minus 4 squares. So this is like 4 by 8. This is a 4 by 8 rectangle minus 4 squares. Okay, and this one is 5 by 11. I think that's right. 5 by 11 minus 4. And this one is 6 by 14 minus 4. Okay, so I think I see a pattern here. 4, 5, 6 for the first dimension. So this is going to be a 7 by something. And this is 8, 11, 14. Looks like that goes up by 3. So 7 by 17 minus 4, whatever that is. Let's see, 7 times 17, 70, and so it's 119 minus 4. It's 115. Okay, I'm pretty sure. Might want to double check that calculation. But I think our step 4 is going to have 115 squares. Boy, this is growing pretty rapidly. Let's go ahead and analyze the numbers here. These are a little bit annoying to analyze because they're kind of big, but we can do it. So we'll look at the step number and the number of squares. So in step 1, that's 4 by 8 minus 4, 32, 28. Okay. In step 2, 5 times 11 is 55, minus 4 would be 51. And in step 3, let's see, 6 times 14, that's 84, minus 4 is 80. And then we've got step 4, we're predicting 115. So let's go ahead and take the differences here. Let's see, 51 and 28, is that 23? And then 80 and 51, 29. And then 115 and 80, that'd be 35. So we're not getting constant. We didn't expect that. It's not a linear pattern, clearly. We can take the second set of differences. 29 minus 23 is 6, and 35 minus 29 is also 6. Aha. So we're getting a constant in the difference of the differences, which means this is quadratic. And our leading coefficient is this constant, this difference we got in the second order differences divided by 2. So our leading term is going to be 3x squared. And at this point, you could try plotting out 3x squared in each one of these, although in step 1, that's just 3 blocks. You've got so much more left over. So I don't know how fruitful that will be. I think I'm actually going to use this intuition we had at the beginning and translate that into an equation. So we have this rectangle, so it's two things multiplied by each other, the length and the width, right? So length and width. And it looks like one of the sides, the width here, is going up by 1. So it's always just 3 more than the step number, right? So step number plus 3. I'm going to write that as x plus 3. So in step 1, that'd be 4, and we've got a 4 by 8. In step 2, the 2 plus 3 is 5, so we got a 5 by 11. So that's how that part works. The length is a little trickier. It's going up by 3. And when something goes up by 3, that rate of change, you've got to multiply the x by that 3. But then you might need to add something more. So in step 1, 3 times 1 is just 3, but we've got 8. So we actually have to add 5. Let's double check that this part works in step 2 and 3. So here, 3 times 2 is 6, plus 5 would be 11. That's what we get there. In step 3, 3 times 3 is 9 plus 5 is 14. That's what we get there. Okay, so this is working. So this is the rectangle if it were all filled in, but we've got those 4 spots missing. So we also have to remember to subtract 4 from that. Now this equation is perfectly adequate the way it is. You could leave it like this. I'm going to FOIL it out and see what we get. So 3x times x is 3x squared. There's that leading coefficient we expected. And then 5 times x is 5 and 9. So that's 14x. And then we've got 15 minus 4 is plus 11. Okay, so this should be our equation. And I don't think we have to test it too much. You can go ahead and do that. We saw that it came directly from our visual intuition here, so I think this is going to work. Let's just try it in step 1 just to make sure we didn't misplace a sign or something like that. So this would be 1 squared times 3 would be 3 plus 14 times 1 is 14 plus 11. So that's actually 14 and 14, and that's 28. And yes, that's how many we got there. You can test this with step 2 and step 3 if you like, but I'm confident that this is our equation. Now, to get the number in step 43, we've got to plug 43 in here. So this is going to be 3 times 43 squared plus 14 times 43 plus 11. Oh my goodness. So 3 times 1849. And let's see, what's 14 times 43? That'd be 430, and then another 160, 172. Is that 602? And then plus 11. And the 1849 times 3, that is going to be 5,547. Okay, plus the 602 plus 11. What does that come out to? 6160, I think. Double check that for me, add those numbers up, make sure I did that right, but I think we're going to get 6,160 squares in step 43. That is a big pattern. Well, how did that go for you? Did you get 115 for step 4? I think that it was pretty hard to get, actually. Did you find a way to get to an equation? I'd be curious to hear about that too. Let me know. Thanks, everybody.